Today I'm going to answer a couple of quick questions from two students. The first question is by Arnold Heckers, and he's asking about the video on small signal amplifiers, and his question is the source AC or DC? Well, I'm not quite sure what you're asking, so let's draw the circuit real quickly here, and I'll speculate on what your question is. Two directions I can go here, so we'll see if I can answer your question. So here is the small signal amplifier, and of course, if you have not seen the video on small signal amplifiers, be sure to go watch it. It's linked in the description below. Make sure you understand what we're talking about before we get there. So here are the various components. Here's a microphone going through a coupling capacitor, our collector resistor, our base biasing resistor network, and our emitter resistor. I'm going to leave the emitter capacitor out for this particular explanation. And there's our output. And the question is the source AC or DC? Well, do you mean the signal source, which is the microphone, or do you mean the source that's powering the amplifier? So first of all, the source that's powering the amplifier is definitely DC. Almost everything actually runs on DC. I'll just put plus 10 volts here because that's a reasonable voltage to put there. And either we're going to run this from a battery or something that simulates a battery, such as a power supply. So this would definitely be DC. Our power is distributed in AC, but most things use DC, with the exception of maybe things such as toasters and electric motors. But most things want DC, so your power supply takes the AC from the wall, lowers the voltage to something more reasonable, and converts it to DC to power whatever circuit we are running. So that would definitely be DC. Nothing much else to say about that. The signal source, of course, is alternating current. Now, we do have DC amplifiers, but this would not work as a DC amplifier because of the coupling capacitor here and because of the basic design. But the microphone would produce alternating current. I like to use my pin as an analog for a microphone, and remember, inside there is a diaphragm that moves when vibrations in the air hit it. And particular types of microphones work a little differently, but basically we have a diaphragm. When it moves one way, it causes current to flow in one direction, and when it moves the other way, it causes current to flow in the opposite direction. So as that diaphragm is going back and forth, or in this microphone here, we have current going this way, then that way, then this way, then that way, back and forth and back and forth. So that would be alternating current. However, once we get here, we have a mix of AC and DC. So if this is 10 volts, I would speculate I would design this to be about 5.7 volts right there, which would, it depends on other things I'm not going to go into right now, but I'm just off the top of my head going to say that. That would be more true if I did not have the emitter resistor, but let's move on. So I'm going to have a DC bias set up by these resistors to give me about 5.7 volts here. This microphone is going to give me just a few millivolts of alternating current, so it's going to be changing voltage, all different frequencies, but I'm just showing a simple sine wave here. And as we move it through here, what I end up with, well, let's take a quick look at this. This is our AC coming from the microphone, and it's centered on 0 volts. So the voltage goes up when the current goes one way, and the voltage goes down when the current goes the other way, so we get positive, negative, positive, negative. But when that transfers over here through the capacitor to the alternating current, pretty much looks like a short circuit. It's frequency dependent, but we think of it as acting like a short circuit to alternating current. A capacitor, whenever we change the voltage across it, it conducts for a short time. If you look at my video on charging capacitors, you can see how that works. We start charging it, it looks like a short circuit. After a time, it looks like an open circuit. But in the case of AC, the voltage is changing all the time, so it constantly looks like a short circuit. So whatever AC voltage I have here is the same over here. The difference is that the center, let's just draw this again, is centered on that DC voltage, which would be, make room here, plus 5.7 volts. So the AC voltage is the same. Let's say it's just about 100, let's say 100 millivolts. To minus 100 millivolts. So that would be 200 millivolts peak to peak. Same thing here. Goes 100 millivolts above my 5.5 or 5.7 volts and 100 millivolts below my 5.7 volts. So it's going to be going up to like 5.8 volts and down to 5.6 volts, 5.8, 5.6, 5.8, 5.6. But notice that the deviation is the same of 200 millivolts, just that this one is centered on 5.7 volts, that one's centered on 0 volts. And so this is still technically alternating current because I have that periodic changing of my voltage. It's just mixed with some direct current. So that's the answer there. The source that's powering it is definitely DC, but my input source is AC. Whether it's a microphone or some other kind of pickup, it's going to be some kind of alternating current. Now the next question comes from Joseph Workman, and it's a pretty short question with an unfortunately short answer. In a previous video, I talked about the speed of electricity, and I showed that in I think it was a 14 gauge wire, that if we have 1 amp of current going through a 14 gauge wire, it will take something like 16 minutes for the electrons to actually move 1 inch. Sorry about the imperial units here, but I'm in America. It's just the way my brain works. But an inch is what, about about 2 centimeters. So it takes about 16 minutes for the electrons to move that far. And you can do that by calculation because we know that 1 amp of current would be 1 coulomb of charge every second. And 1 coulomb of charge would be carried by 6.24 times 10 to the power of 18th electrons. So let's take a look at that. 6, 2, 4, 1, 2, 3, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Put some commas in here just for good measure. There we go. So that's how many electrons are carried in 1 coulomb of charge. What is that? I got a million, billion, trillion, quadrillion, quintillion, 6 quintillion electrons. So that's how many electrons we have per thousandth of an inch in that wire. So we say 1 amp of current is this many electrons per second. How many seconds does it take for that space of electrons in 1,000th of an inch to move all the way across? Well, it takes, of course, 1,000 seconds, and that would be about 16 minutes. So by simple calculation that anybody can do, I can calculate that it will actually take about 16 minutes for the electrons to move 1 inch, or about roughly 2 centimeters in the wire. Now, Mr. Workman asks me to do an experiment to see how fast the signal moves. Well, this is not the signal moving, this is the electrons moving. The signal moves at somewhere between 1/2 the speed of light and 95% of the speed of light, depending on the configuration of the wires. So if we have just 2 parallel wires, just off the top of my head, I could do some calculations if I looked up how to do it, but we're going to see anywhere from 0.6 times the speed of light to maybe 0.95 times the speed of light of the actual wave of energy. It's like a train. If you start the train up, well, the whole train starts at once. Well, not really, because the locomotive starts to move and it pulls, and it's assuming that all of the slack is taken out of all the couplings, it's going to move as a sound wave. The front of the train starts to move first, and then a wave of energy goes through the train, starting the rest of the train moving, and that moves at the speed of sound through steel, which is something, thousands of miles per hour. It's much faster than the speed of sound through air. So it seems to instantaneously move, but actually it's a wave that moves down it. That's the signal. Same thing with electricity. We turn on a circuit. So I put a battery here, have some wires. Let's put the switch over here. There's a light bulb. I turn on the switch, and a wave of energy travels at somewhere between around, I said 0.6, somewhere around half the speed of light to almost the speed of light through that wire, and the electrons all through the wire all start moving at once, just like a train. All moves at once, even though it's a wave that goes through it. It doesn't all start at once. It takes a split second for that wave to move down the train. It takes a tiny, tiny amount of time for this wave to move air and get everything moving. And then once everything's moving, the light lights up. But the actual movement of electrons in a 14 gauge wire, assuming that's 1 amp of current, is going to take about 16 minutes to move every inch, or every couple of centimeters. So the electrons move slow, but if I open the switch, they all stop at once, and there's a wave of stoppage that goes through there. So that travels nearly the speed of light. Can I set up an experiment to test that? No, I don't have any kind of instrumentation anywhere near precise enough to measure that kind of speed. We're talking about something, up to 95% of the speed of light. We're talking about making it from the Earth to the Moon in a couple of 2.5 seconds. So I have no kind of instrumentation that could ever measure that. I just have to go by what is published, which would be the velocity factor. Let's get some of this out of the way. So if you look at some kind of a cable that's used in places where this is important, there's a term called velocity factor. And that basically is how fast the signal moves through that cable compared to the speed of light. So let's say we have a coaxial cable. We're sending radio signals through, and it has a velocity factor of 0.95. Well, what's that telling us is that a signal moves through that wire at 95% of the speed of light. I believe that Ethernet cables have a velocity factor of about 0.5, just off the top of my head. I think ribbon cables have a velocity factor of around 0.6 or something like that. But you have to go by that because somebody else with instrumentation I don't have has measured that, and I have to take their word for it. So no, I can't do that experiment. I just don't have the instrumentation. But thanks for the question. If you found this video useful and informative, please give me a thumbs up down below. It really helps the channel. And subscribe, because that not only informs you when I put new videos up, but it really helps the channel also. And a big thank you to my patrons at Patreon. I could not make these videos without your support. If you want to help me put these videos online and keep real vocational education free at vocatomy.net, you can go to patreon.com/join/vocatomy and pledge your support. And again, a big thank you to my patrons who make this possible, and a big thank you to everyone for watching.